Okay, we're going to look at rational functions. This is part 2. We have an example, f of x equals x plus 3 over x plus 1. We're going to go through our graphing tools and see how each of these things are going to help us sketch a graph of this function. We're going to start with the domain, and for the domain, we are interested in what value we want to exclude so that the denominator doesn't equal 0. So we can just take that denominator and x plus 1, and we say that cannot equal 0. We subtract 1 from each side, and then we get x not equal to negative 1. Okay, the next thing we're going to look at is actually the vertical asymptote. So the vertical asymptote is the line x equal to a where a is the x value excluded from the domain of f of x in its fully reduced form. Okay, so this is a definition of vertical asymptote. It's a line, and that's a vertical line where that value a is an x value excluded from the domain of the function, given that the function is in its fully reduced form. Now, the example that we have is in its fully reduced form. We don't have any factors in the top and bottom that we can cancel out, so it's in its fully reduced form. So that means that we have a vertical asymptote of x equal to negative 1. Okay, so if we want to start the graph of this function, we can start by putting in that vertical asymptote. Remember that the definition of the vertical asymptote is as x values get closer to it, the function is going to go to positive or negative infinity. So the vertical asymptote is not part of the graph. It just gives us a place where we know that the function is going to either go up or go down, positive or negative infinity. So here is the vertical line, and we're going to label that it is x equal to negative 1. Okay, let's look at the next thing. We're going to look at x-intercepts. Okay, to find x-intercepts, we just need to set the numerator equal to 0. And solve for x. The only way that we're going to have the function equaling 0 is if the numerator is equal to 0. So in this case, our numerator is x plus 3. We set that equal to 0, solve for x, we get x equals negative 3. Okay, we can plot that point. Let's see, I guess I need one more hatch mark there. And we can plot that point for that x-intercept right there. Okay. Now let's look at the y-intercept. So this is where we are going to evaluate f of 0. That's going to equal the y-intercept. Okay. All right, so for our example, f of 0, we're going to get 0 plus 3 over 0 plus 1. So we get 3 over 1, or just 3. So our y-intercept then is 0, 3. So if we plot that, all right, we get that point right there. So we have our x-intercept right here, we have our y-intercept right there. Okay. So the next tool that we are going to use is the horizontal asymptote. Okay, so far we've looked at the y-intercept. Okay, so I'm just going to highlight the tools that we've looked at. We've looked at the vertical asymptote, and we've looked at the domain. Okay, so next tool that we're going to look at is the horizontal asymptote, and we're going to need to do a little bit of explanation here. So I'm abbreviating the horizontal asymptote as HA. Okay, so reminder that the horizontal asymptote is the fixed value of y that the function equals as x goes to plus or minus infinity. So as x goes to plus or minus infinity, right, this is the end behavior, f of x, or y, goes to some value b, then the horizontal asymptote is y equal to b. Okay, so let's give kind of an explanation of how to find the horizontal asymptote. Right, so to find HA, the horizontal asymptote. So the horizontal asymptote is going to depend on the degree of the numerator and the degree of the denominator. So we're going to start by saying that we're going to let n equal the degree of the numerator polynomial. I'm going to abbreviate numerator here. And then we'll let m equal the degree of the denominator. And I'm going to abbreviate denominator. Okay, so we've got 3 different cases. If we compare those 2 degrees, we can have that the degree of the numerator is less than the degree of the denominator. And if that is the case, then the horizontal asymptote is the horizontal line y equals 0, or the x-axis. Like we looked in our example yesterday, the reciprocal function. The second case is when they are equal, when the degree in the numerator is the same as the degree in the denominator. Then the horizontal asymptote is the horizontal line y equal to the leading coefficient in the numerator over the leading coefficient in the denominator. All right, third case is only other thing that can happen is n is greater than n. The degree in the numerator is greater than the degree in the denominator. Well, in this case, there is no horizontal asymptote, but we need to check for a slant asymptote. All right, we are not going to go into that today. That's going to be for another video. Okay. All right, so those are our 3 cases. All right, you definitely want to write those things down because that's going to tell us what kind of horizontal asymptote we have. And if we now go back to our example, so just a reminder, our example is f of x equal to x plus 3 over x plus 1. And we want to find the horizontal asymptote. So we want to determine what the degree is. So for the numerator, the degree is 1. All right, the highest exponent we have on x is 1, and the degree in the numerator is also 1. Okay, so we have the case number 2 where n is equal to m. All right, so that means that our horizontal asymptote is going to be the leading coefficient in the numerator. Well, that is a 1. Over the leading coefficient in the denominator. Well, that is also a 1. Okay, so our horizontal asymptote is 1 over 1 or just 1. Okay, we want to put that on the sketch of our graph. So let's go back up here to our graph. Our horizontal asymptote is this horizontal line where the y values are all equal to 1. So y equals 1, just like that. Okay, now we're going to talk about the last step in graphing our rational functions, and this is something called critical values. So I have the graph so far, which we just have the y and the x-intercept, and then we've got our horizontal and vertical asymptotes. This actually gives us a lot of information just based on the definitions of those vertical and horizontal asymptotes. The one last piece is to identify where the graph is positive, where it's above the x-axis, and where it's negative, where it's below the x-axis. So that brings us to critical values. And critical values are, well, there's 2 different things that count as critical values. First of all, they are x-intercepts, and I'm going to abbreviate that, and vertical asymptotes. Okay, so for our example, we have critical values of x equal to -3 and x equal to -1. Okay, because we've got x-intercept at -3, we have x, or vertical asymptote at -1. Okay, so we've identified what they are. Now we need to know, well, what in the world do they tell us? So the only place, or let me be more technical or mathematical about it, the only values of x for which a function f of x will change from positive to negative, or the other way, negative to positive, is at a critical value, and I'm going to abbreviate critical value, CV. Okay, so the only place that this graph is going to change from being above the x-axis to below the x-axis is at one of these 2 critical values, and the other way around, from above to below or below to above. Okay, so the way that we determine that is to test out different values that are on either side or in between those critical values. So what we're going to do is create a number line for x values. Okay, so these are just x values. We're going to put our 2 critical values on here. Okay, so you can see how that takes all the x values and it breaks it up into 3 intervals. So the interval from -infinity to -3, the interval in between -3 to -1, and then the interval -1 to positive infinity. Okay, the other thing to know is that this is the only place it can change sign. So we have to just test one value in each of these intervals to see if it's positive or negative. Okay, so we're going to, the next step here is to test one value of x in each interval to see if f of x is greater than 0 or less than 0. Let me write that the same way I wrote it. Okay, and then that's going to tell us what the graph does for that entire interval. Okay, so for the interval negative infinity to negative 3, let's choose the value x equal to negative 4. So we are going to plug negative 4 into the function. We'll take negative 4 plus 3 over negative 4 plus 1. All right, so we end up with a negative 1 over a negative 3, which is positive 1/3, and what we care about is that it's greater than 0. Okay, so that means that this graph, the function, is going to be above the x-axis for all values of x from negative infinity to negative 3. All right, so I'm just putting a little plus sign there to remind me of that. Okay, let's look at our next interval. And let's choose x equal to negative 2. Actually, I'm going to use a different color so it is separate from what I just did. Let's use green. Okay, let's go x equals negative 2. So we're going to evaluate f of negative 2. Okay, plugging that in, we get negative 2 plus 3 over negative 2 plus 1. And that gives us 1 over negative 1, which is negative 1. That's less than 0. Okay, so that tells us in this interval from negative 3 to negative 1, the graph is going to be below the x-axis. Function values are negative. Okay, last one from negative 1 to infinity. I'm going to go back to red. And let's use the value x equals 1. So f of 1, we're going to get 1 plus 3 over 1 plus 1. So that is 4 over 2, or equal to 2. All right, that's positive. So on that interval, we're going to be above the x-axis. Okay. The other thing that we get from testing out these values is that we actually get points that we can plot, right? We just, we plugged in an x value and we got a y value, so that's going to give us a point for each of these. So let's go back and just write down what those are. So this is getting really cluttered, but for this first one, we plugged in a negative 4, so our x value was negative 4. Y value was 1/3. So that's a point that we could plot. And for the second interval, we plugged in a negative 2 for x, and we got a y value of negative 1. There's another point we can plot. And for the last interval, we plugged in a 1 for x, and we got a y value of 2. All right, so we can plot all those points. Okay, so let's see if we can get those on our graph. And so negative 4, 1/3. So that's going to be, extend my x-axis. Negative 4 is about right there. And then 1/3, let's just put that right about there. And then we've got negative 2, negative 1. So that's the point right there. And then our last one was 1, 2. So 1, 2. Okay. So now we get to sketch this graph. So we can kind of see on in that the lower the left lower part, we can see those points kind of lining up, and we can connect those. Now, remembering what that horizontal asymptote is telling us, it's telling us that as x values go to negative infinity as we go to the left, the graph is going to approach that line but not touch it or cross it. And then our vertical asymptote says as x values get closer to x equal to negative 1, there's only two choices. The graph is going to go to positive infinity or negative infinity. Well, since we know on that interval from -3 to -1, we know that it has to be negative. There's only one choice. Okay, so this is, as we get closer to that vertical asymptote, the graph is going to go down. Function values are going to go to -infinity. Okay, so we get that shape. All right, now we go to the other points that we have. This time, let's start with the point on the left. Again, as we go to the vertical asymptote, as x values gets closer and closer to -1 from the right, there's only two choices. We're going to go to infinity or -infinity. But from -1 to infinity, for x equal to -1, for x values greater than -1, we have to be positive. We have to be above the x-axis. So that means we're going to go to positive infinity. So our graph is going to look like that. And then if we connect the others, as x values get large, we're going to get closer and closer to that horizontal asymptote and not touch it or cross it. All right, so my graph is a little wonky, but that's going to be a smooth curve that looks like that.